Light is nature's means of providing energy and conveying information. One of the most remarkable ways humans have learned to harness light is through photography.
Crickle, the view is beautiful, isn't it?
Yeah, I wish I could freeze this moment.
So let's talk about how light has been perceived over time. Light waves had evolved from waves into a complex concept of wave-particle duality. In the 18th century, it was proven that light existed in discrete packets called photons, which photoelectric effect helped in progress within wave theory. The photoelectric effect is the emission of electrons from a material, typically a metal, when it is struck by electromagnetic radiation, like light. That has given us the formula E is equal to hf, whereas E is quantized energy, H is Planck constant, value is 6.63 times 10 power negative 34 joule second, and average frequency. Now, let's talk about the threshold frequency, which is the minimum frequency of light to eject electrons. So, photoelectron emission depends on the frequency of the light and not intensity, differing from its wave properties. No matter how bright the light is or how long you shine it on the metal, no electrons will be emitted if the light frequency is below threshold frequency. Why? Because one photon can only transfer its energy to one electron. Therefore, each photon must individually carry enough energy, hf, to free an electron.
The threshold frequency is determined by the configuration of atoms on the surface of a material. In a metallic structure, electrons are delocalized. They can move freely within the structure, but are still electrostatically attracted to the positive metal ions, meaning that energy is required to remove them. Imagine this as a tank with electrons flowing freely at the bottom. To remove an electron, a minimum amount of energy called the work function must be supplied. Let's trace this back to the energy of a photon. Now, if the frequency of the photon is equal to the threshold frequency, it has just enough energy to overcome the work function and successfully liberate an electron, but the electron just stays there. If the frequency of the photon is greater than the threshold frequency, then after overcoming the work function, the excess energy is converted into the kinetic energy of the electrons, causing the photoelectron to move away from the surface with a velocity. Now, based on this observation and according to the principle of the conservation of energy, we can derive the photoelectric equation where the energy of the incident photon is equal to the sum of the work function and the kinetic energy of the emitted electron.
However, inside a camera sensor, something slightly different happens. To understand how a camera sensor detects light, we first need to look at a semiconductor. Silicon is used as a semiconductor in most camera sensors. In a semiconductor, electrons do not occupy isolated energy levels as they do in individual atoms. Instead, they exist in energy bands. Most electrons are found in the valence band where they are tightly bound to atoms and cannot move freely. Above it lies the conduction band where electrons have enough energy to move through the material and carry electrical current. Separating these two bands is the band gap, a forbidden range of energies that electrons cannot occupy. An electron must gain the least amount of energy before it can move into the conduction band. When a photon with enough energy strikes the silicon, it excites an electron across the band gap into the conduction band, leaving behind a hole. Together, this form was known as an electron-hole pair. This progress is called the internal photoelectric effect because the electron remains inside the material instead of being ejected from it. These free electrons can then be collected and measured, allowing the sensor to determine how much light has reached each pixel.
Every single time you snap a photo, your camera instantly translates light into billions of zeros and ones. It sounds like magic, but it actually happened in 3 quick steps. You can think of it as a game of counting buckets. Inside your camera, it's the CMOS image sensor, a grid made out of millions of microscopic buckets called pixels, and each pixels contain a tiny photodiode where the photoelectric effect converts light into electrical charge. When you press the shutter, light pours onto the sensor, causing electrons to accumulate in each pixels. Each bucket is filled in a way that more electrons gather in brighter area while dark areas are left with fewer. And then a tiny chip measures how filled the bucket is and then assign them into the brightness value. Then those chips write numbers down into the computer code of zeros and ones and then pieces them together. Now you have a digital photo.